Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA 2021 Combined Science or the Trilogy, Physics Paper 1 Higher Tier. Question number 4 is on the topic of particle model of matter, mainly focusing on practical skills involved in measuring density of objects, which is also required practical. Question number 4, a student determined the density of a cube made of bronze. The student used a balance to measure the mass of the bronze cube. So they're measuring the density. Figure 5 shows the balance before the cube was added. Now, without anything on the balance, it's reading 4.2 grams. What type of error is shown on the balance? Now, the error is to do with the equipment. So what do you call that error? Now, there's two ways of referring to this error. Now, generally, if you have a reading like this, you would press the button called tare in the scale itself, which is basically to return it to the zero value. So you call it a zero error, but you can also call it as a systemic error as well, because the error is to do with the measuring equipment. Any of those answers will give you that 1 mark. How could the student get a correct value for the mass of the cube from the balance? Well, what would you do if you have an error like this? Well, you would press the button to make it 0, right? Or let's say you're measuring a mass of the object and it has to be 10 grams. Instead of 10 grams, it's going to read with this 4.2, it'll read it as 14.2 grams. So what you can do is take away 4.2 from the value that is actually recorded when you add the mass. So let's say when you can't zero it, or you don't know how to zero it, you'll add the mass, add the object on top, and you take away this 4.2 from the reading that is given. So any of these two answers should give you 1 mark. Reset the balance to 0 grams, or subtract the reading shown on the balance from the reading taken. Next question. 4.3. The student measured the length of the bronze cube using vernier calipers and then using a micrometer. Now, vernier calipers and micrometers are two equipments that can be used to measure the length of small objects. Now, it will be worthwhile to have a look at what vernier calipers and micrometers actually look like, because in GCSE, we generally don't use these two equipments very often, and most students wouldn't have actually seen this unless you're in A level. So it's worthwhile to actually Google what vernier calipers and micrometers look like and read a little bit about it so that you understand this question better. But they have given you the information in the table. The vernier caliper, using that, the length is measured as 20.1 millimeter. Now, if you're going to use a ruler, the shortest length you're going to be able to measure it is in 1 millimeter. So vernier caliper gives up to 1 decimal place of a millimeter. A micrometer, on the other hand, is measuring at 20.14 millimeter. So it's actually far more accurate to measure it using a micrometer. Now, I use the word accurate. It's not entirely correct, because the question is asking, complete the sentence. The results in table 1 show that the vernier caliper and the micrometer have different what? Now, it's not accuracy, because it's to do with the number of decimal places. It's to do with the resolution, how precise it is. So they have different resolution. The micrometer has a higher resolution than the vernier calipers. Next question. The student wanted to determine the density of a bronze coin. The student had several identical coins. The volume of each coin was very small. The student added water to a measuring cylinder. Figure 6 shows the student reading the volume of water in the measuring cylinder. So now, in chemistry, mainly we teach you about how to use a measuring cylinder or how to take readings for the volume in a measuring cylinder, and this is absolutely not the right way to do it. So what would you do? Give two changes the student should make to increase the accuracy of the volume measurement. So you wouldn't lift it, you would put it on a flat surface first, and then you would actually record it at eye level. So the answer, place the measuring cylinder on a horizontal surface like a table, then view with eye in line with the level of the water. Without it, you're going to get you're going to have something called a parallax error if it's not read properly. Next question. Describe how the student could use a displacement method to determine an accurate value for the volume of a single coin. Now, if you were to add a single coin into a measuring cylinder, the question is how much. Here they are using a displacement method, so they've mentioned a measuring cylinder, so I'm going to refer to the measuring cylinder here in the answer. So let's say you got 50 ml of water. Now, if you add the coins generally don't really have that much of a volume. So if you add a single coin, if that volume, the volume should actually increase. Now, if that increase is very small, you're going to find it difficult to read the value to get a very accurate value for the volume of a single coin. So what you could do is, let's say you can add about 10 coins or even 5 coins. That way, the increase in volume is going to be bigger. Now, you can work out the difference in the volume and then divide that volume by the number of coins that you've added to get the volume of a single coin. So, for 3 marks, add several coins to the measuring cylinder. Measure the change in the water level in the measuring cylinder. Divide the number of coins. Divide by the number of coins added. So let me bring that slightly up. Measure the change in the water level in the measuring cylinder. Divide let's say divide the increase in volume by the number of coins added to get the volume of one coin. 4.6. Old penny coins were made from a disc of bronze. New penny coins are made from a disc of different metal. Figure 7 shows a disc of metal. So you have the cross-sectional area and the thickness. Table 2 shows information about the discs used to make each coin. So the old penny coin has a mass of 3.6 grams and the new penny also has a mass of 3.6 grams. The density of the old penny coin is 8.9. Density of the new one is not known. The thickness is 0.16 and the new penny is slightly thicker by 0.01 centimeter, 0.17. So the disc used to make the old and the new coins have the same cross-sectional area. Calculate value X in table 2. Give your answer to two significant figures, which should carry a mark if you give your answer to two significant figures. The volume of a disk can be calculated using the equation. So they are giving you the equation to calculate the volume of a disk, which is the cross-sectional area multiplied by the thickness. So they have given us the thickness you will have to work out the cross-sectional area. So let's have a look at how we are going to do this. So for 5 marks, you will need to use more than one equation. So let's start off with the first equation that we need. Calculate value x, which is the density. So remember, density, the symbol for density is rho, which looks like a P. So density equals the mass divided by the volume. Now, in order to find the value of x, you need the mass, which is given in the table. The volume needs to be determined. Now, to find the volume of the new coin, you need to use this equation. Volume of disk is cross-sectional area. So surface, let's say it's a cross-sectional area multiplied by the thickness. Now, they have given us a clue here in this first statement. The disk used to make the old and the new coins have the same cross-sectional area. So they have given us the thickness for the new coin. I need to find the cross-sectional area here so I can work out the volume for the new penny. So how am I going to do that? So I'm going to use this value from the old penny, the density and the mass and the thickness first, these three values to find the cross-sectional area. So let me do that here. So density, this is for the using the old penny. Density equals the mass divided by the volume. The mass here is 3.6 divided by the cross-sectional, the volume, remember, is given by this equation, cross-sectional area multiplied by the thickness. So the area, which I don't know, multiplied by the thickness, which is 0.16, is equal to the density, which is 8.9. So rearranging this equation, the area is equal to 3.6 divided by 8.9 times 0.16. So let's do that as a fraction. 3.6 divided by 8.9. 3.6 divided by 8.9 times 0.16. That gives me an answer of 2.53. So 2.528. Let me write it as up to 3 decimal places. So 2.528. So cross section is 2.528. 2.528 multiplied by the thickness, which is 0.17. This is for the new penny coin. To find the volume, multiply that answer by 0.17. That gives me an answer of 0.429. Now I can use that volume in this equation. Density equals the mass divided by the volume. What was the mass of the new coin? Which is 3.6. So 3.6 divided by 0.429. That should give me an answer of, let's 3.6 divided by 0.429. That's 8.39, and they want the answer in two significant figures, so it'll be 8.4. So the answer is 8.4 gram per centimeter cube. That brings us to the end of question number 3. Is it 3? Question number 4. Thanks for watching. I will see you in the next video.